Okay, we're going to continue on here. We're talking chapter 7. Sounds like a good one. Why not? And last time we talked about types of reactions and ways to sort of classify them. So remember, there's kind of two big sort of umbrellas of classifications of reactions. There are redox reactions, and really redox reactions involve a transfer of electrons. Again, if somebody gets oxidized, they typically will lose electrons. If somebody gets reduced, they will gain electrons. And remember, you can really sort of figure that out by looking at what is really the oxidation state of the elements on each side. But you can also think of it as like the charge. So when you look at one element on the left-hand side versus the same element on the right-hand side of the arrow, there's going to be a change in the charge of it or oxidation state because either gained or lost electrons. And you can use that sort of little ruler type thing or number line to help you. When somebody loses electrons, as we talked about, they then have more protons than electrons, so they will be more positive. So if you see the charge from the left-hand side of the arrow to the right-hand side, kind of move in the positive direction here on the number line, then that substance is going through oxidation. Bless you. If somebody gains electrons, which is the definition of reduction, they then will have more electrons than protons, so they will become more negative. So as you're comparing the same element on opposite sides of the arrow, if it is becoming more negative, it is going through reduction. They always occur together. So if somebody's being oxidized, somebody else is being reduced, and vice versa. And as we talked about last time, kind of one of the nice things about that is if you could for sure identify who's being oxidized or who's being reduced, by default, pretty much the opposite thing is happening to the opposite guy. Under the big redox umbrella, falls more specific ways of classifying reactions. Those are your, again, synthesis, your decomposition falls under there. Basically, one thing makes two things, synthesis, two things make one thing. Single replacement falls under there. And combustion basically all fall basically under these sort of the big redox umbrella. And again, these are sort of more specific ways you could classify really the same reaction based on what is going on. Now, sort of the other big classification of reactions are double displacement reactions. And always in a double displacement reaction, you always have two ionic compounds. And again, that's how you know it's kind of like a double displacement thing happening. And always in this situation, the two positive ions will basically switch partners, and they basically just switch partners. And on the other side there, we get two new ionic compounds. And the result of this is one of two things typically will happen. Perhaps one of these guys makes a solid, which is known as a precipitate, and a more specific classification of a double displacement reaction that produces a solid or precipitate is known as a precipitation reaction. Again, a more specific classification. And occasionally as well, one of these guys may actually make water. And that usually occurs in a more specific reaction of an acid-base neutralization reaction. And when you take an acid plus a base, you always get two things. You get what's referred to as a salt plus some water. A salt's an ionic compound. And water always comes from the H plus from the acid and really the OH minus from the base. It's really a double displacement reaction. And those two guys basically hook up from opposite guys and make water. What's left over is what makes your ionic compound or your salt in that case. And really, under that big umbrella of double displacement, those are the two types of more specific classifications that you have. This basically accounts for really the three reasons why a reaction takes place to begin with: transferring electrons, formation of water, or the formation of a solid. Those are, again, are pretty much pretty much all reactions boil down to one of those three things basically happening in this case. Now, after we talked about that, we got into some important calculations, and we were talking about something, maybe. Let me do that and stop writing things. We were talking about Avogadro's number. Remember, Avogadro's number is basically what 1 mole equals. And again, the abbreviation for mole is MOL. And again, that is not molecules. And 1 mole of anything does equal 6.022 times 10 to the 23. Now, the units that go with Avogadro's number, which is this number here, can vary. Most of the time, you're going to see atoms or molecules are probably the two most common units that you will use with Avogadro's number. It really is a conversion factor that allows you to go between those units. So, if you have moles, you would multiply by Avogadro's number to get to atoms or molecules. The moles will cancel and give you atoms. If you have atoms or molecules, you would divide by Avogadro's number. And that would get you to moles. So that's really, again, your conversion factor to go really from moles to atoms or molecules. As we talked about as well, it's really important not to use Avogadro's number in every calculation ever. Again, and you want to look for kind of the keywords as we talked about, which is, did they give you a number in atoms or molecules? Or are they asking you to solve for something in atoms or molecules? Again, if they are not giving you any of that information, you probably shouldn't be using Avogadro's number. The other sort of conversion, which is probably more important in a sense, does come from the periodic table. And it is the number on the bottom, which we earlier saw as the atomic mass, but a more usable sort of unit that we used from it is what is known as the molar mass. And the molar mass has units of grams per mole. And it's more useful because we measure things in grams. So that's, sort of instead of AMU and stuff like that. Now, this is a conversion factor that allows you to go from moles to grams or grams back to moles. Basically, is the molar mass is your conversion factor. Again, you get that from the periodic table. Typically speaking, as we talked about last time, it's like 4 significant figures. You want to take off that bottom number is what you want to use. Now, you could do this for just an element by itself. So the molar mass of hydrogen would be 1.008 grams per mole. And you can use this as a conversion factor. The number stays with the grams, and it's always 1 mole, basically. So the mole is always 1, and the number stays with the grams part. So you could use this as a normal dimensional analysis type conversion like we did, where you do it like that, or you could flip it around, obviously, the other way as well. And again, you could set it up dimensional analysis, opposite units cancel. And again, it kind of takes care of the math part of it for you. You could also apply this obviously to a molecule as well. And if you did something like oxygen and hydrogen in water, again, what you would do is basically just add up all the parts from the periodic table. So there are 2 hydrogens. So you would take 2 times the molar mass of hydrogen from the periodic table. You would then add it to the 1 oxygen's molar mass, which is 16. And again, basically just add it all together, and that would get you 18.02 grams per mole. And that would be the molar mass of water in this case. Also, again, could be used as a conversion factor. You could use it again like that. Or you could flip it around and put the moles up on top. Once again, as you can see, the number does stay with the grams part always when you do molar mass. Now, how they all relate together is, remember that as you go from grams, say, to atoms or molecules, really the unit that ties these together are moles. Moles is really the thing that kind of ties both of those units together. And if you got to go grams to moles, that's the molar mass from the periodic table. Moles to atoms, Avogadro's number. If you're starting with atoms or molecules and need moles, Avogadro's number. Moles to grams, molar mass from the periodic table. So again, that's sort of how you go through there. 1 mole of whatever it may be, say hydrogen, would have 6.022 times 10 to 23 atoms of hydrogen, and that would have a grams of 1.008 grams. So again, that's basically how they are all related to each other. Any questions on any of that stuff we talked about last time? Yeah. So let's take a look at maybe another example here. Let's just say we had let's say we had 4.55 moles of CO2, and we want to know how many grams of CO2 that is. And again, I want to give you some info that might be helpful. 12.01 for carbon, and oxygen, as I had up there, 16. How many grams of CO2 do I need to use Avogadro's number here? I do not. Again, a reminder, that is moles, not molecules. So no Avogadro's number needed. We're basically going moles to grams in this case. And again, our conversion factor to do that is from the periodic table here and getting the molar mass. And in this case, we do need to add up the molar mass here for CO2. Once again, all we're going to do is basically just add up all the parts from the periodic table. Again, there's one carbon, which means it has a molar mass of 12.01, which again is the number on the bottom of carbon on the periodic table. We also have 2 oxygens, so we'll go to periodic table there and we see 16, and we'll add 2 or multiply 2 times 16 grams per mole, which will basically take care of the oxygens there. And that will give you something like 4401 grams per mole as the molar mass. Once again, this is really something we could use as a conversion factor. So if we needed it in this problem, we could have flipped it around and also used it as a conversion factor as such. So in this case, I think that's really all we need. We're going to start with our 4.55 moles of CO2. Once again, we're going to take a dimensional analysis approach because that makes hopefully everything a little bit easier. We could see that the moles are on top. So again, in this approach, it's just opposites to cancel. So that makes our decision hopefully pretty straightforward. We want to go with that guy right there. That's going to put my moles in the opposite location. And again, since this is dimensional analysis, we always know math-wise, we're multiplying the top and we're dividing the bottom. So that's always, again, a benefit of setting it up this way. So you always know mathematically what you should be doing with these numbers. That means really in this case, we're just multiplying, I think. So 4.55 times a 4401. There's really nothing on the bottom there to divide by. Everything's 1. That'll get us something like 200 grams of CO2. I do kind of need the decimal as that's 3 significant figures there to keep it. Any questions on that calculation there? So again, as I mentioned, probably in chemistry, grams to moles, moles to grams is used a lot. Yeah, it's probably the most. Not a lot of Avogadro's number in a lot of cases outside of the chapter it's in, but usually grams, moles, moles to grams, molar mass from the periodic table. Definitely a lot of things use that. Any questions on up there? About 2 slides. We'll get there. Yeah. Yeah. One more thing I did want to talk about with this type of conversion is sometimes we may not be interested, for example, in the entire thing that we're dealing with. So for example, here we have CO2. We could actually use CO2 as our example. So we'll just use this guy. So let's say we started with our 4.55 moles of CO2. And let's just say we're not really interested in CO2 as a whole, but maybe we're just interested in one of the elements that are present. And we want to know, say, how many moles of oxygen are there. Maybe we want to know how many atoms of oxygen there are, or maybe we want to even know how many grams of oxygen there are in that many moles of CO2. So one place that you could get a good sort of relationship or conversion factor from is actually the formula itself. So when we look at CO2, and more specifically, we look at these numbers that are on the bottom. Obviously, it's not written, but that's 1, obviously, usually, right? These do represent what are referred to as the moles of each of those guys. So 1 mole of carbon, 1 mole or 2 moles of oxygen by itself. So we could actually get sort of a mole to mole relationship just using the equation. So we could say that in 1 mole of CO2, the entire thing, there would be just 1 mole of carbon. And again, that comes from the kind of the one on the bottom, basically. And we could also say in 1 mole of CO2, the entire thing, there is how many moles of oxygen? Yeah, just 2 moles of plain old run-of-the-mill oxygen by itself, basically, in this. So we could actually pull some mole-to-mole relationships from the actual equation. And since these are equalities for each of these, we can write our normal kind of 2 conversion factors that we could use in a problem. So really, in this case, we could use one of these 2 in a problem. We could also use, you know, these 2 as well in a problem. So again, from the actual equation, we could get these sort of conversion factors. So why is this helpful? Well, in this case, we are starting with moles of the entire thing, and we ultimately want to end up with just oxygen by itself. So this is a conversion factor that's going to allow us to go from the entire thing to just that element of oxygen. We do it the exact same way. We just set it up dimensional analysis and get everybody to cancel correctly. So we would do that by taking 4.55 moles of CO2. Again, we want to actually go from CO2 to oxygen, which means from the formula, we actually want to use this relationship, which gives us these 2 conversion factors over here. And once again, we want to go opposite. So we want to get rid of moles of the entire thing and want to be left with just oxygen by itself. So again, opposite speaking here, we would want to go with this conversion factor that we actually got from the chemical formula itself. That will get rid of moles of the entire thing. And we take 4.55 times 2. That's going to give us 9.10 moles of just oxygen by itself, right? And again, that is a way we could go from the entire thing to one of the elements. We could just as easily, if we were interested in carbon in this case, use the relationship of carbon and do a same calculation, basically. Now that I actually have it in moles of just oxygen by itself, I could actually answer the other questions as well. So let's do the atoms of oxygen. So I'm in moles of oxygen. I want atoms. What should I use? Avogadro's number. Again, atoms is the key word there, right? We want to get to atoms. So we could set up again in dimensional analysis. We want moles to go on the bottom so they cancel. And we want Avogadro's number there to go up on top so that we're left with atoms. Again, we're going to multiply and divide here. And in this case, we're basically just going to multiply that number. So since I got on my calculator here, 6.022 to the 23, that gives me something like 5.48 times 10 to the 24 atoms of oxygen. And that would actually answer that question right about there. Now, for the last question, I want how many grams of oxygen that would be. Which number should I start with in that calculation? These are the moles, right? I want to go moles to grams. I don't want to go backwards and have to undo atoms, right? Since I already have the answer. So since I already have the answer, I want to actually start with 9.1 moles of oxygen. And how would I go from moles to grams? What would I need? Moles to grams is big thing behind me. Molar mass from the periodic table, right? So that is where I would then once again go and find oxygen and get my number on the bottom, which tells me is 16.0 grams per mole is our molar mass of oxygen. And again, we would use this as a conversion factor, 16 grams per mole. 9.1 times 16 gets me about a $1.46 grams there of oxygen in this case, and that is there. So you may come across some problems. Sometimes books like to do that where they're maybe not interested in the entire thing you're looking at, that compound, but they may be interested in just one of the elements. So you could always use a formula as like a conversion factor, a mole to mole conversion factor, which means in order to use that, you do have to get whatever number you're starting with into moles. Yeah, so it's got to always be moles so it cancels out correctly. In this case, we started with moles, but if we started with grams of CO2, you would first need to take it to moles and then continue on with the calculation so that everything cancels out correctly. Any questions on that sort of variation there of that problem? Okay, so now that we talked about balancing equations and we talked about grams to moles, we're now going to kind of put them together to answer your question, which is, can we figure out in a chemical reaction, if we know how much we start with, how much product we'll make, or even if you know how much product you made, can you back calculate and figure out how much reactants you started with? And the answer is yes, and that's what we're going to talk about here, which is calculations from chemical equations. I was almost right. I think it was 2 slides. That's pretty close, I think. So when we do this, this is what is also known as stoichiometry. Big fancy word. It's just basically a conversion factor is what that means. So stoichiometry is the calculation where you use an equation that's balanced. You maybe, like I said, know how much reactants you're starting with, and you can do a calculation to figure out how much products you should produce. Or if you know, again, how much products you produce, you can actually back calculate and figure out how much reactants you started with. You can actually figure out everything in the reaction. If you just know kind of one piece of information, you can make a calculation. For example, if you have 2 reactants and you know how much of one you have, you can figure out how much of the other you need to actually react. Also, if you have like 2 products and you can figure out how much of one product you made, you could also figure out how much of the other product you would make as well. So it's kind of like a calculation that lets you figure out everything about the equation. Again, as long as you kind of know one piece of information about, how much you're made or started with. So the way that we do this is, first off, always it needs to be a balanced equation. So that should always be like your first step, no matter what you do, pretty much in chemistry, but definitely in these problems, you always want to look at the equation and you want to make sure it's balanced. I would say, again, if you see numbers in it, it's probably balanced unless somebody's trying to trick you, but usually it should be balanced. If you don't see coefficients, you definitely probably should take a pretty hard look at it and just double check that it is balanced, or if it's not, that you need to. Now, when we look at these coefficients, they do represent different things. They can be the molecules of each of these. So these coefficients here, we could say there's 2 molecules of H2 react with 1 molecule of O2, gives you 2 molecules of H2O. We could also use what you use in stoichiometry, which is sometimes referred to as the mole to mole relationship. And we could say that this is 2 moles of H2 gives me 1 mole of O2 and 2 moles of H2O. These numbers are simply just the coefficients. There's no magical place where these numbers are coming from, other than after you balance the equation, they're actually just the number in front of the formula in the equation. Yeah, so there's no like calculation to figure out those numbers. You just need to make sure it's balanced. The last one is one that we don't use too much, but it is that conservation of mass, again, which is why we balance equations like we talked about previously. If you start with 6 carbons, you'll end with 6 carbons. Again, they may be in different things, but since carbon's 1201 on the left and also 1201 on the right, you'll have the same mass of reactants and products because it's the same stuff. We will basically be using this relationship here. That mole to mole relationship is essentially what we're going to use. So this, again, is, like I said, what is referred to as stoichiometry. And really, stoichiometry, as we'll talk about in just a second, as I mentioned, is really nothing more than a conversion factor. And really, instead of like looking it up in a table to find the conversion factor, or looking on the periodic table to find the conversion factor, you actually find the conversion factor in the balanced equation. So that's where you look basically just to find your conversion factor. The reason you typically have to do that in stoichiometry problems is they typically will give you a piece of information about that reaction that you're frankly not interested in. You're actually interested in somebody else. So you need a way to convert from, say, like a reactant to a product, or maybe you need to convert from like a product, the information they gave you, to a reactant, or maybe they give you information about one reactant, you need to figure out about the other reactant as well. So it's really just a conversion factor because the information you frankly have is not really what you want, and you got to get over there. And there's no book for all the different chemical reactions we have that says, okay, this one is this relationship and this relationship. So it's just really where we get that. Now, when we do this stoichiometry, just so you're aware, let's just say we had A plus B goes to C plus D. Now, sometimes people think when we do these sort of calculations, it always has to be between somebody on the reactant side to somebody on the product side. And that's always the way you have to do the calculation. And it's not. You can't definitely do a relationship between reactants to products. Just like if you started with products, you could also do the relationship going across the arrow. You don't even have to cross the arrow, as I've been talking about. You could actually just do the relationships between the two reactants. And you could also do the relationship between the two products without going across the arrow. So again, sometimes people think it's always got to like go across the arrow and do that relationship, but you could do this type of stoichiometry calculations, as we'll see, with really anybody in the equation. So it doesn't necessarily mean you have to go from one side to the next. Commonly, we do go from reactants to products or products to reactants, but you definitely could stay on the same side of the arrow and do the same sort of calculation. So the units that we use can be really any units, but for us, it is going to be really moles. And if your units are not in moles, you need to pretty much do this. You need to get them from 2 grams and usually go to moles. And at the end of this calculation, a lot of times we need to go from moles back to grams. So what we were just talking about, right? If I want to go from grams to moles or moles to grams, what conversion factor do I use for that? That is, again, the periodic table molar mass. So that calculation, like I said a second ago, all over these type of calculations. Yeah, so this is going to be used a lot here. And you actually go both ways a lot of times in these calculations. You'll kind of go grams to moles, and at the end, take moles back to grams. So you'll be having to kind of go both ways with that. Again, very rarely will you probably use Avogadro's number in one of these calculations. It's pretty much going to be always kind of the molar mass from the periodic table when you do so. So there are several steps to follow when you do stoichiometry problems. I would say probably in your case, most of the time you probably will have the equation given to you. But just in case it's not, like we talked about when we were talking about just balancing equations and so forth, you do want to make sure that you write all the correct formulas first, and then you balance the equation. You then want to convert whatever they gave you into grams, and then convert those grams into moles. You then want to actually do the stoichiometry part, which is the mole to mole relationship. And then you want to convert those moles into whatever you're looking for. For our purposes here and our stoichiometry problems that we come across, you pretty much could cut this down to 4 basic steps that, kind of like when we talked about drawing Lewis structures, if you follow these 4 basic steps in order, it should get you to the right answer at the end. Yeah. So if you just kind of follow these steps and do it. So the 4 basic steps really are what we see on here, but here are really the 4 sort of basic steps for a stoichiometry problem. Pretty much it all starts with, you want to always make sure you have a balanced equation. And again, I would say probably most of the time in your case, you're going to have the equation. It's just a choice of is it balanced or not. That's what you definitely want to look at. None of this calculation will work correctly if the equation is not balanced. So if you skip that step, you're just messed up your whole calculation. So again, that's why you got to go in this order and do it this way. Once you have it, you want to take whatever units they give you. And in our case, the nice thing about our problems, you'll probably give them one number only in the problem. Yeah. So one type of number with some type of unit. It to moles. And again, that's going to eventually be the molar mass there that's going to get you to moles. The third step that you want to do is actually the mole to mole relationship. It is actually the big stoichiometry move that people freak out about, but it is actually just this move. And this is, you will go to the balanced equation and you will find the mole to mole relationship that you are interested in. So you may be asking, like, how do I know which one I'm interested in? So it's a very simple sort of solution for you guys in terms of which one you're interested in. So for example, let's just say we have this equation here, 2a plus b goes to 4c, right? And this is like balanced equation. We'll go with it. Now, let's just say in a problem, we were told, hey, we have, you know, 30 moles of C, and we want to know, how many moles of A, for example, right? So when we would get to the equation here, we would get to step number 3. We would go, all right, they gave me C, so I'm clearly interested in C, right? And they also we're looking for A, which means I am clearly interested in A. And from the balanced equation, how many moles of A are there? 2. And how many moles of C? 4. And again, it is just the coefficient, yeah? And that is the relationship of C, or 3 here, where people, again, kind of freak out sometimes, but that is, again, where you get it, is just the balanced coefficients. This, again, is going to give us, as we'll talk about shortly, basically 2 conversion factors that we could use that we essentially got from the equation. So those are the 2 conversion factors in my made up one. And again, the reason we need this is because we have information about C, but ultimately we want to get over to A, and we need a way to convert over to A, and it is just the equation where we're going to allow us to do that. If you successfully do 3 correctly, which hopefully you will, you should always be at this point in the units of moles. So you should always be sitting in the units of moles. And at this point, this sometimes can be an optional step, or it may be a step that you need to do. And you want to convert these moles into some other unit. So again, most commonly, I would say probably for you guys on the back end here, maybe moles back to grams. Yeah, using again the molar mass from the periodic table. It's a very common sort of ending for this type of calculation. By the way, if you were asked for just moles, you'd be done after 3 because you would have the answer in moles. You just put a box around it. So these are really the 4 steps that you should follow in that order every time you do a stoichiometry problem. Now, if something is done for you, just go forward. Don't go backwards. Yeah. People, for some reason, want to unconvert things, right? So, for example, like I started with moles. It doesn't mean I got to take it back to grams just to go back to moles. It's already done for me. I can skip number 2, right? It's already in moles. So, I don't need to kind of undo the wheel there and come back to it. So it's a very common sort of step. So always go forward, never go backwards. Yeah. In these 4 steps. And again, if something's done for you, just go to the next step if necessary. Any questions on that there? Yeah. You can, but typically you don't, because you don't want to mess yourself up by doing that. It mathematically, it'll come out the same, obviously, right? So like, for example, if I put 4 over 2 and I did, 2 over 1, it's going to mathematically come out the same. But you probably don't want to do that because you might kind of mess up the relationship or do something incorrect. So I would recommend perhaps not doing that. Not that it's wrong or you wouldn't get the right answer, but you might mess yourself up by accident trying to do that. Yeah. Other questions? All right, so let's talk a little bit more about this, how we get all these good things here. So let's just take this equation right here, a real one here, A, B's, no. We got CO. So we got 2CO plus O2 gives us 2CO2. So once again, from this one equation, we could get a lot of relationships or equalities from it. So for example, if we wanted the stoichiometric equalities, which is a fancy way of saying our conversion factors, we're going to look at the coefficients here. And I can see from the coefficients that for every 2 moles of CO, I get how many moles of O2 in there with it? Yeah, if there's nothing written, it's implied to be 1 in chemistry, right? So we would have 1 mole of O2. If I put in there 2 moles of CO, how many moles of CO2 will I get out? It is 2. It is, again, just a coefficient there. So I would get 2 moles of CO2 out. If I put in there 1 mole of O2, how many moles of CO2 will I get? I will still get 2 moles of CO2. So from this one equation, we have basically 3 equalities that we could use in a problem. Each of these equalities, like any equality we talked about, like in chapter 2, if you remember back then, you could get 2 conversion factors from. So for each of these equalities, I'll go here, we could write 2 conversion factors. So 2 moles of CO over 1 mole of O2. And all we're doing is just making a fraction, basically, and then flipping it. So 1 mole of O2 gives us 2 moles of CO. From this relationship, we could get 2 moles of CO over 2 moles of CO2 are 2 moles of CO2 over 2 moles of CO. And lastly, here from this relationship, 1 mole of O2, 2 moles of CO2 are 2 moles of CO2, 1 mole of O2. These are all the conversion factors, right, that we could get from this equation. So from this one singly balanced equation, we have 3 relationships, and we could have actually 6 different conversion factors that we could use in a problem. Will we use all 6 of them in a problem? I hope not. Otherwise, you're doing something really wrong. Yeah, so you should not use all 6 of them in a problem. They're just available to you to use. You probably are only going to use one. Yeah, just pick the one that you need, basically, in that case. You never want to use both of them together because, again, you'll undo probably the calculation. So just probably ones you're going to pick. So, for example, if we look at this guy here, let's just say in this case here, just to show you all the steps here with this guy. Oh, we have all that written. Let's say that we started, actually not started, let's say we produced in this case. I don't know, we'll go 15 grams of CO2. We want to know how many grams of O2 did we start with? So we want to basically figure out how many grams of O2 if we actually produce 15 grams of CO2. So as soon as you have a question like that, the first thing you think of is stoichiometry. And then you should think of those 4 steps. So let's just go through those 4 steps. First step is balance the equation, right? So step number 1 is already done for us. We want to balance the equation. So that was already done for us. So we go off to step number 2, right? Step number 2 is to take whatever units you have, basically, and get them into moles, right? So step number 2 is basically convert to moles. And the only actual number I have in my problem here is which number? This is the only one that has a number, right? And that is 15 grams of CO2. And my next step here at step number 2 is to get those guys to moles. So once again, if I have grams and I want moles, what am I using? I am using the molar mass from the periodic table. I'm not going to recalculate because we just did, I think, a second ago. It is that 4401 number, just like we calculated back here, I think, was it at somewhere there was. There it is. That would be what we calculated somewhere here was 4401. I think it was actually this one right here. There it is. 4401. That's what we calculated previously. So I'm just going to use that number, but you would calculate the exact same way we did previously, obviously. So all right, so what I want to do now is take my 15 grams. I'm going to do the molar mass from the periodic table, which is our 4401 that we did previously. And again, that's basically 1 carbon at 1201 plus 32 for the 2 oxygens. We want to go opposite, right? So grams need to actually go on the bottom so that they cancel. Once again, grams are up on top. Moles of CO2 go up on top there. Grams will cancel. We're going to multiply what's on the top and divide by what's on the bottom. So you don't actually have to get an answer at this point, but I will so you can see all the steps if you like. So 15 divided by 4401 gives me something like 0.34083. I'm going to take a couple extra digits, not round too much at this point because we're going to kind of continue on at this point. That is step number 2. I took whatever they gave me and basically converted it to moles. So again, whatever unit it's in, you got to get it to grams, and then grams to moles is sort of the ending part of that sort of calculation. I am now sitting right about here. I now have moles of CO2, right? I'm over here, but I'm not really interested in that, right? Ultimately, I'm interested in which one? I'm interested in grams of O2. So I need a way to get rid of the CO2 and end up with the O2. This is pretty much what stoichiometry is. We need a conversion factor. And that is our third step, which is we do want to do the mole to mole relationship, right, from the equation. And we did that a second ago. So obviously, I would look at this relationship, right, from the equation, which is the coefficients. And that gave me an option of really two conversion factors. Which one should I use? The one on the left or the one on the right? Which one's going to leave me with O2, which is what I'm looking for? It is the one on the left, yes, because this is still up on top, the moles, right? And we want to get rid of moles in this case of CO2. So I'm going to use that conversion factor for step number 3 and go 2 moles of CO2 gives me 1 mole of O2. That right there is the big stoichiometry move, yeah? A little conversion factor that you get from the table, yeah, or from the actual equation. That's going to get rid of the moles of CO2. That now is going to allow us to get to O2, and I'll divide that basically by 2. Again, we're going to multiply what's on top, divide by what's on the bottom. So we're going to actually divide by 2 in this case, and this will get me 0.17042 moles of O2. First off, any questions up to there? If my question was asking for moles of O2, what should I do at this point? I should put a box around it and go on to the next question because I would be done at this point, right? So again, don't overcomplicate it. Make sure you stop at the right moment. We don't need to do that in this case because we're actually not done with this calculation, right? Because we do not want moles of O2. We actually want grams of O2, right? So we do need to do the fourth step, which is take those grams to some other unit, and in this, I'm going to take it to moles. So now I have moles and I want grams. What should I use to convert that? The molar mass of what? Of O2. So very important at this point, we're no longer CO2ing, right? We got rid of it. We're at O2. So we do need to go back to the periodic table and calculate the molar mass of oxygen, which is O2. And that would be 2 times 16 grams per mole, would give me 32 grams per mole. And that again is the conversion factor that we're going to use for the fourth step. And again, I'm just going to take this number here and we'll go 0.17042 moles of O2, 32 grams of O2 up on top. Moles need to go on the bottom so that they cancel. Again, that is still up on top, and those moles will cancel. And we will end up with, we'll go 5.45 grams of O2 in this particular case. Those are the basic 4 steps of every stoichiometry problem. Balance the equation, convert to moles, do the mole-to-mole relationship, and convert those moles to some other unit. You will again always hit the right answer if you follow those steps in order. I did it in parts and I did get an answer after each step, which is perfectly fine to do. Just don't round too much after each step until the end. If you want to combine all those steps and just keep going in your dimensional analysis, you absolutely can. You could go from here to here to here all in one calculation is perfectly fine as well. If you don't really need an answer in between, you can do that. Whatever way is easier for you, do it that way. Yes, I would recommend. Any questions on that there? It does not matter how complicated the equation looks. It doesn't matter what number you have. Those 4 steps in a row, and you should get to the end at the right step there. All right, let's take a look at one here maybe. This is pretty much what we just talked about, so I'm just going to kind of slide through it there. Maybe there's a problem. Here we go. Why don't you try this one? Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed if you react 5.32 moles of lithium with water? In this particular one, we actually don't have an equation. We have everything in words. So just to remind you, you want to just get all the right formulas down first. So lithium metal by itself would be Li. Reacts with water, which is H2O, right? And to form means you put an arrow. Hydrogen gas, that is what formula? H2, not just H, yeah? So remember, you'll have a trouble balancing if you don't put the H2 there. And lithium hydroxide, LiOH. So that is the unbalanced equation. I'll let you pick it up from there. So follow those same 4 steps that we just talked about. We want to balance the equation. We want to convert to moles. We want to do the mole to mole relationship. And then we want to take moles to some other unit if necessary. So follow those 4 steps, see where you end up. Okay, let's take a look, see how you're doing. So once again, trust me when I tell you these 4 steps are what you want to follow. And again, in this case, we did have everything in words, so you probably won't have too much of that. But in case you do, a reminder, you do want to get everybody down in the right formulas, just like you're doing nomenclature. And then we want to go back and balance it, right? So first step here is balance the equation. We didn't do that. So to balance this equation, I don't know, maybe like a 2, and like a 2. I feel like I'm just throwing 2's down. Hope that's right. So we got 2 lithiums on the left, 2 on the right, 4 hydrogens on the left, 4 on the right, and 2 oxygens on the left and right. So we should be balanced at this point. And now we want to take whatever information they gave us, which again, in your guys' problems, will pretty much just be one piece of information. And in this case, you got 5.32 moles of lithium. Ultimately, though, we're not interested in lithium. We do want to eventually end up with hydrogen, right? We want to end up over here, basically, right? So again, we know it's a stoichiometry problem because what they gave us not what we want, right? We want to get over there. So step number 2 is to convert to moles. Do I need to do that in this case? I do not. It's already done for me, right? So again, don't undo things. Yeah, so we're good to go. We got number 1 done. 2 was already done, so that's nice. So number 3 is we want to go to the equation, actually do the stoichiometry. So again, we're just frankly looking for the 2 things we're interested in. One thing should always be whatever they gave you. So they gave you lithium, so clearly we're interested in this guy. And the second thing you're interested in is what you're trying to find, which in this case is hydrogen, right? No sense worrying about anybody else in that equation except for those 2, since those are the 2 things you're interested in. We could get our mole to mole relationship from that. And again, it is just the coefficients, which means we have 2 moles of lithium will give us how many moles of hydrogen? 1. Again, it is just the coefficient that is there. That's going to give us, again, our sort of 2 available conversion factors to use. 2 moles of lithium, 1 mole of H2, or 1 mole of H2, and 2 moles of lithium. So now we got everything we need for the 3rd step. We're going to obviously take our result of the 2nd step, and we're going to actually do a calculation now. 5.32 moles of lithium. Once again, not written like that, but again, moles are up on top in this case. That should hopefully make our decision easy. Conversion factor on the left or conversion factor on the right would be the correct one here. Which one do you think? Which one's going to get rid of lithium, which we no longer want, right? Because we ultimately want to get over here, right? It is the one on the right. Yeah. Again, that is in the opposite location. That is going to give us our 2 moles of lithium. And this is, again, the big stoichiometry step right about here. And again, since we set this up with dimensional analysis, I don't even have to think about the math because I know everything on top gets multiplied, everything on the bottom gets divided, right? So that's always a constant in terms of the math part of it. So basically what we're doing is taking 5.32, we're dividing it by 2, basically, in this case. And that's going to give me 2.66 moles of hydrogen in this case. That will take care of step number 3. Do I need to do step number 4 in this case? I do not, because the answer we're looking for is moles of hydrogen. And that to me looks like moles of hydrogen. So I should just put a box on that. And again, sometimes you may not have to do that 4th step. A lot of times you do, but you may not if you're looking for moles. So you'd be done at this point. By the way, if I wanted grams, just for curiosity's sake, what would I need to go from moles to grams in this case? The periodic table, molar mass of H2, right? So if we were asked for grams, we would just have to do the additional step. And again, we weren't in this case, and find the molar mass here of H2, which would be something like that, right? So 2 times 1.008, and obviously the moles would cancel and you'd be left with grams. So it wasn't asked for that in this case, but that would again be where you would get it, molar mass from the periodic table. Once again, hopefully you can start seeing a pattern 1, 2, 3, and 4 if necessary. Yes. Thank you. Thanks a lot. Okay, we're going to continue on. So we're talking about, again, stoichiometry here. So we want to just kind of continue on and follow those 4 steps. So let's do a few more examples here, I think. All right, that's one we just did. All right, why don't you try this one here? Same equation. In this case, though, we want to know how many grams to will we 81.75 grams of lithium. Let me give you some numbers that will probably be helpful. Lithium from the periodic table, 6.941, oxygen 16, and hydrogen 1.008. Again, follow the same 4 steps that we've been talking about. We want to balance the equation. We want to convert to moles. We want to do our mole to mole relationship, which is our stoichiometry. And then we want to take those moles to some other unit. All right, so take a few moments. Okay, so let's take a look, see how you're doing. Again, we want to follow the same 4 steps. We could definitely recognize it as a stoichiometry problem. We're given one piece of information. We got an equation. We're looking for H2 just like we did previously. So step number 1 here is already done as we did it obviously in the previous problem. So the only piece of information given to us is 81.75 grams of lithium. I'm going to now go to step number 2. Do I need to do step number 2 in this case? Step number 2 is convert whatever they gave me into moles, which means yes, I do. This is a grams to moles conversion, which, as we've been talking about, is the molar mass. So I would go to my periodic table there and find my conversion factor for lithium in this case. And that is basically 6.941 grams per mole is our molar mass of lithium. So step number 2 here, we're going to convert to moles. We're going to do dimensional analysis. And again, that guy not written with anything basically there is up on top. That means that we actually do need to flip our molar mass as a conversion factor. We need grams on the bottom so that they cancel. Remember, opposites cancel. Moles of lithium. Again, I know when I set it up this way, I'm multiplying and everything on the bottom gets divided, which means in this case, I'm dividing 81.7, if you punch it in right better, 81.75 divided by 6.941. Once again, you don't really need to get an answer at this point, but I will just so you can see all the steps. Again, I'm not going to round too much at this point. Again, I'm just kind of clean it up there at the end. I now have moles of lithium, which is our second step. We now remember pretty much the whole point of stoichiometry is, in this particular example, we were given information about lithium, but again, we're not really interested in lithium. We are again interested here in our H2, and that really is what the stoichiometry allows you to do, is to get that conversion factor. So step number 3, we go to that balanced equation, and once again, it is just the coefficients to get the relationship. So the coefficient in front of lithium is 2. So that means I get 2 moles of lithium for 1 mole of H2, kind of the same relationship we used previously as well. That again will give me 2 options in terms of conversion factors. And again, if we just write them down so you can see them here, we could do that or this. Lithium. So taking my number I got from the previous step and just kind of continuing on with it, I'm going to go 11.7778 moles of lithium. Once again, that is basically up on top. So that should hopefully also make it an easy decision that here we will need to use the conversion factor there on the right, as that will get rid of lithium, which we no longer want, and take us basically over there to hydrogen using the equation as a conversion factor. So 2 moles of lithium, 1 mole of H2. Moles will cancel. Once again, dimensional analysis setup, multiplying and dividing, right? So we're going to divide basically our number there by 2, going to get us 5.8889. Again, not rounding too much at this point. First off, any questions up to there? Am I done with the problem at this point? I am not, because again, this time we are actually looking for grams. So we do need to do the 4th step here. And again, at this point, we would need the molar mass. We do want to remember that we are no longer dealing with lithium. We are now at H2. So we will need the molar mass of H2. Again, we could go back to our table here, periodic table, and get that. So the molar mass of H2 going to be 2 times 1.008 from the periodic table for our 2 hydrogens. 2.016 grams per mole will be our molar mass. That's going to set up our 4th and final step here. We're going to take our number from the previous step. Once again, it is basically over 1, which tells us the moles are on top. That does mean to get rid of the moles, we do need to put the moles on the bottom so they cancel. That would give us moles of H2 on the bottom, and the grams would go up here up on top. Once again, dimensional analysis, multiplying the top, dividing the bottom. We're basically going to multiply, in this case, 2.016, and that's going to get us 11.87 grams of H2. I would go probably 4 significant figures based on the only number really in the problem, which was 4 significant figures in this case. Hopefully, once again, you can see same 4 steps: balance equation, convert to moles, mole to mole relationship, moles to some other unit. Once again, you absolutely, like I said earlier, could go from here directly to here, directly to here with no answers in between if you want, and it's perfectly fine as well. So if it helps you to get answers in between, get answers in between. Just again, don't round if you do too much until kind of the end and clean it up. Any questions on that? What does this number really means? This number really means that if you did this reaction and you tossed in there 81.75 grams of lithium, everything went perfect. Rarely does, but everything went perfect ideally. You would get out there 11.87 grams of H2 should be produced as a result of this reaction. That is why it is also sometimes called the theoretical yield. And that is basically your maximum amount of product that you would make in this reaction. Again, if everything went perfect, no side reactions, you didn't spill anything along the way, you know, everything would be perfect. That is how much product you should get out. Any questions on any of those steps there? All right, now that you're professionals, let's do a few more. Huh? See here. All right, let's try this one here. You got 765 grams of C6H12O6 and it's consumed by the body. What is the mass? So we're looking for how many grams of CO2 would be produced. So some numbers that will be helpful: carbon 12.01, oxygen 16, hydrogen still 1.008. Once again, no surprise, follow the 4 steps here. Balance the equation, convert to moles, do your mole to mole relationship. Okay, let's take a look, see how you're doing. Once again, here, got a stoichiometry problem. That should automatically tell you we're going to follow our steps. So first step there, we want to balance the equation. I see coefficients, so I'm going to hope really good that it's balanced. It should be, hopefully. So the only thing given to us is 765 grams of C6H12O6. Step number 2 is convert to moles. Do I need to do that? Yes. So again, I need to go to the periodic table, add up all the parts. 6 times 12.01 for our carbons, plus 12 times 1.008 for all of the hydrogens that's in there, and 6 times 16 for all of the oxygens, going to give 180.2 grams per mole. And again, we're going to use that as our conversion factor. And a reminder, usually about 4 significant figures is where we round off there our molar mass. So again, we're going to start with what was given to us. We know it's over 1, which means the grams are up on top. That tells us that we do need to put the grams on the bottom here to cancel. 180.2 grams per mole C6H12O6. Again, we also know multiplying and now dividing. So we're basically going to take 765 and divide it by that number. That's going to give us 4.2463. Again, I'm not going to do too much rounding at this point. And that will take care of step number 2. Step number 3 is really the stoichiometry part. So this is where we go to our balanced equation and we find the 2 things we're interested in. So since we were given this guy and we're looking for CO2, those would definitely be the 2 things we're interested in. Again, this is going to be just the coefficients. So although I scribbled on that guy there, it is 1 in front of that. C6H12O6 gives us 6 moles of the CO2. And again, that's what we're going to use as our conversion factor, because ultimately we want to go from there over here, basically, right? And that conversion is going to allow us to do that here from the equation. So taking the number that we left off with in the previous step, 4.2463 moles of C6H12O6. Again, opposite cancel. So moles of the C6 is up on top. That means it needs to go in the opposite location to cancel. And that would put our 6 moles of CO2 up on top. Again, multiplying and dividing. So we're basically going to multiply here by 6 in this case. And that is going to get me about 25.4779 moles of CO2. And that just did the stoichiometry part of the calculation in this particular case. That is not where I want to end, right? Because I'm not looking for moles. If it was, I could put a box on it. But here we're actually looking for grams. So we do need to do the 4th step, which is take those moles, in this case, to grams. And that would be the molar mass of our CO2. And we calculated a number of times today. So once again, that is that 4401 number that we did in a number of examples. So I'm just going to kind of use that. And I'm going to do step number 4 right here with that number. Moles again are on top, which means the moles of CO2 got to go on the bottom. The 4401 grams of CO2 need to go up on top. Again, multiplying and dividing. So we're basically going to multiply this by 4401. And that is going to get us here 1121 grams of CO2. Truth be told, this number we only had was 3. So probably like 1120 grams if we're still shooting for sig figs at this point in the problem there. And we got something like that. You should probably still be shooting for sig figs at this point in the problem. Again, hopefully you can see the pattern we've been talking about. Balance the equation, convert to moles, mole to mole relationship, moles to some other unit. By the way, here we ended in grams a couple of times, but you could be asked for any unit. You might have to do a few conversions. Maybe they want, some weird unit, pounds or something. You might have to do a few more, but it's just basically conversions at that point. So I would say most often moles to grams is probably where you'll kind of end there at the end. Any questions on stoichiometry? Okay, that wraps up chapter 7, the exam after spring break. So we'll get going on this. So chapter 8 involves gases. So obviously when we're talking about gases, we are talking about the state of matter where pretty much everybody has broken apart from one another. So they're flying around, and as they're flying around, they're causing collisions. And the collisions is what we associate with gases that cause our pressure, which is obviously typically what we associate with gases a lot is the pressure. Obviously, as we'll talk about, more collisions, more pressure, less collisions, less pressure involved in that. So let's talk about substances that usually exist as gases under normal conditions. And when we talk about normal conditions, we're really talking about room temperature conditions. They are sometimes referred to as standard conditions, but not STP. That's something a little bit different. And what we talk about that under kind of normal conditions is like room temperature type conditions, 25 degrees Celsius, pressure is 1 atmosphere. Those are kind of standard conditions. And under normal conditions, compounds go into the gas phase, and that's because they're held together by that electrostatic attraction, positive, negative attraction, right, between the ions. That is probably, again, the strongest attraction you could have. You could heat the heck out of an ionic compound. It will never go into the gas phase. It will just start to melt before it will actually go into the gas phase. So if you do an experiment, for example, you have salt water and you evaporate off the water, and you just keep heating the salt that's left over, the sodium chloride, it will start to just melt before it will actually go into the gas phase because of that really strong attractive forces. Now, molecular compounds, which are guys that are held together by sharing of electrons, are a little bit different. They can be gases kind of right out of the gate. Things like carbon monoxide is a gas, carbon dioxide, ammonia, hydrogen chloride gas, methane, which is what comes out as you light the Bunsen burner. One of the major differences, though, between sort of molecular compounds and ionic compounds in terms of gases is a majority of molecular compounds are liquids and solids at room temperature. The difference between them and ionic compounds is they can much easier be converted into gases. Probably the prime example is water, right? We could take water, which is normally found as a liquid, and you could heat water, not super strongly, right? But just enough with like a fire, right? And you will get it to go into the gas phase. And that's because when you take something like water, which is a polar molecule that we talked about, oxygen more negative, hydrogen more positive, when you have different water molecules together, they are held together by what is known as hydrogen bonding. And hydrogen bonding is what is known as an intermolecular force, and it is much weaker than, say, like ionic bonding, which is an intramolecular force. So what happens with water when you go to heat it is the bond between the two different water molecules actually breaks first, and off they go into the gas phase. Now, that's different than if you took just one water molecule where the sharing of bonds, like covalent bonding, there's sharing of electrons. This is what is known as an intramolecular force within the molecule. And those are always stronger than an intermolecular force, like what holds two water molecules together. We know that because if it was the opposite way around, when you would heat something like water, you get alphabet soup, it would just fall apart, right? All the hydrogen and oxygen would fall apart. Probably not a great idea if you're heating it at that point. If you got hydrogen and oxygen being made, you might not get to the pasta part of it if you're boiling water to make pasta in that case. So what happens is, because this weaker intermolecular force, the bond that holds these two water molecules, actually is just to 100 degrees Celsius, and you could get them to basically break apart. So the stronger that molecules are held together, the less likely you're going to find them in the gas phase, and the weaker they're held together, very often you'll find them in the gas phase. That's why a lot of organic molecules, which are nonpolar, when an organic molecule and another organic molecule are together, they're held together by like the weakest interaction known to man, pretty much, which you just look at it, they're just going to break apart. And that's why things like methane, propane, butane, those are all gases, right? And we use them and they light up and stuff like that. That's also why when you use organic chemicals, they're sometimes referred to as being volatile, which means you just open up the liquid and they go right into the gas phase pretty quickly, which is why they usually shove all that stuff in a fume hood when you're using that, so you're not inhaling all that stuff. Because in addition to going to the gas phase, a lot of organic things are also very flammable. So if you happen to have a Bunsen burner on when that's happening, that's also not a good idea as well. So when we talk about gases, there are certain ones that we should be familiar with that obviously come as gases. A lot of those diatomic elements that we talked about, hydrogen, nitrogen, oxygen, fluorine, and chlorine, they are gases in their natural sort of state when they're by themselves. Ozone is also a gas, O3. And of course, our noble gases here in group 8. These are what are referred to as being monoatomic. They come as ones, basically. So they basically come as one atom is how they naturally come. So here on the periodic table, everybody that's sort of colored here in this kind of purplish thing, how they normally come is pretty much in the gas state. So this is an important sort of distinction when we talk about a gas and we also talk about a vapor. So a gas is usually referring to something that is normally found in the gas state under normal conditions, like every day, sort of 25 degrees Celsius, 1 atmosphere. A vapor, on the other hand, is something that is normally found in the solid or liquid state, but it can be converted into the gas phase. And that's why when we talk about water in its gas phase, we oftentimes talk about it as water vapor, because it normally is a liquid, right? And you can convert it to a gas. And we don't call it water gas because it just kind of sounds funny, I guess, when you say it that way. But water vapor is sort of what we refer to it as. Now, how do we measure pressure? Well, we do use a barometer. And a barometer is, well, a classic barometer. They usually don't have too many of those anymore at schools. A classic barometer is basically a pool of mercury. That's why they don't have them here anymore usually. You might still have one upstairs, I'm not sure. But it usually has a kind of glass tube in it. And as atmospheric pressure kind of exerts on it, mercury rises, as they say, in the tube. And you can measure the actual reading of the pressure in that tube. 3 very common units of pressure that we deal with a lot is 1 ATM. An ATM is an atmosphere. 1 torr, which is named after the guy who invented the barometer there, is equal to 1 mmHg. mmHg is millimeters of mercury, because the barometer used to be made out of mercury. And on the side of the barometer was a ruler where you could measure it in usually inches or millimeters or centimeters, like a ruler on it, mercury. So that's where that sort of name comes from. They are a 1-to-1 conversion, which means if you need to convert between those 2 units, just change the unit, keep the number the same. Basically, it will not change. The relationship, though, between all 3 of those units is here. 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. So 760 is your magic number to kind of do the conversions. If you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760. Again, you're going to multiply. Or if you have torr or millimeters of mercury, you're going to divide by the 760. So that is, again, your kind of two conversions there. The atmospheres will cancel. The torrs will cancel there on the bottom. So you're either going to multiply probably by 760 or divide by 760, depending on which way you need to go. Any questions on that there? Here's a much prettier picture of a barometer. Kind of looks like my bad drawing. That's there. All right, let's talk a little bit about a gas law here to finish up on. And the first gas law we're going to talk about is what is known as Boyles Law. And pretty much all gas laws have three variables we deal with: pressure, volume, or temperature. So pressure, volume, or temperature is typically what we look at. And Boyle dealt with the idea of pressure and volume, and he held constant temperature. So temperature was held constant here. And what he found was that when you have a high pressure, that's usually a result of a very small volume. So they run opposite of each other. So if we just think about our gas molecules in this very small volume, there's probably a fairly good chance there's going to be a lot of collisions happening, right? They don't have a lot of room to move around. You're going to have a lot more collisions, and you're going to see the pressure actually increase. He also saw that the pressure went down as the volume went up. And that is because if we draw our space for our gas molecules a little larger volume, they now have a lot more room to fly around in, and it's going to take longer for collisions to occur. Less collisions, pressure comes down. So that gives us Boyle's law, which is P1V1 equals P2V2. This is kind of a before and after type of situation. The units here do not matter in the sense that the pressure could be any unit you want as long as they are the same on both sides. And the volume could also be any unit you want as long as they are both the same on each side. And you can solve for, you'll have three of the four basically. Yeah. It is. So as one goes up, the other goes down basically. Yeah. That's it. And by the way, to move this across the other side and with all these gas laws, just to finish up here on, you could think of it as a fraction, right? If you need to move something to the other side, it always ends up in the opposite location. So let's just say, for example, I wanted to solve for V2. P2's got to go to the other side. It's up on top. It ends up on the bottom, and V2 would equal P1 V1 divided by P2. So with all these gas laws, if you have to move anything across the equal sign, it always ends up in the opposite location. Whatever you're solving for should always be up on top by itself. Yeah, so it's always got to be on top. If you have it on the bottom, you're doing 1 over it. So it's got to always be up on top by itself. Things always move in opposite locations as you go across the equal sign. Any questions on that there? All right, let's lay it up.